carbon intensity. So we remember this idea of efficiency, where when you put 1,000 megajoules into a power plant, you may only get 350 megajoules out as useful work or electricity, and the rest will be wasted heat. In this case, your efficiency would be 35%. If we look at the temperatures involved, we may find that we get a Carnot efficiency of 73%, which means that given the two different temperatures, 73% is the highest efficiency we could hope for with a perfect machine. The 35% that we actually get, the first law efficiency, is only 48% of what we could hope for if we had a perfect machine. And then we could say, what about power? Well, if we put in 1,000 what about power? If we put in 1,000 megajoules per second, that would be 1,000 megawatts or a gigawatt that we put in, and we get 350 megawatts out. We also remember the carbon intensity of fuels, where natural gas has the lowest carbon intensity and wood has the highest. This is the amount of carbon dioxide emitted for the amount of heat produced. But what if it's not heat we want? What if it's electrical energy? What do we do then? Well, we recognize that the amount of electrical energy we generate is not equal to the amount of heat, but we have to multiply by the efficiency of conversion. This right here is the carbon intensity of the fuel. And so in fact, the carbon intensity of the electricity we produce is equal to this thermal carbon intensity of the fuel, but we have to divide by the conversion efficiency because we get less amount of electricity out for the same amount of carbon dioxide emitted if we have to convert the heat to electricity. And so then we can look at the carbon intensity of different forms of electrical generation. So we remember that natural gas can use a combined cycle and produce efficiencies as high as 65%, but coal only uses a single cycle Rankine, and its efficiencies are much lower. And so while we look and we see coal has about 2/3 more carbon per megajoule in heat, when we convert it to electricity, we can see that coal has almost 3 times the carbon intensity as producing electricity from natural gas, as far as grams of carbon dioxide per megajoule of electricity. Now, we normally don't talk about electricity in terms of megajoules, so we remember a kilowatt hour is 3.6 megajoules, and here might be the units we'd use in grams of carbon dioxide per kilowatt hours of electricity. What about cogeneration? I mean, what if instead of just dumping this in the ocean, we found a way to heat water with it, let's say with 85% efficiency, and then instead of 650 megajoules of wasted energy, we'd have 550 megajoules of heated water for our use and only 100 megajoules of wasted heat. And then we'd have a total efficiency of electricity plus the heat co-product, giving us 90% total efficiency. And this would greatly reduce our carbon intensity because for the same amount of carbon emissions, you would be getting a lot more energy. So cogeneration is using heat to provide you with two services, whatever they may be. Usually one is electricity. Combined cycle, is that the same as cogeneration? No. Combined cycle is running two cycles that both produce electricity, one working off the waste heat of the other. Where cogeneration is using a fuel to provide you generally with combined heat and power, so that would be electrical power, combined cooling heat and power, where you can use the waste heat or the heat co-product to heat something or actually drive an absorption cooler and run an air conditioner. Now the thing is is, for instance, Diablo Canyon, 2 gigawatt facility, generates electricity for 3-4 million people. Can we provide heat for them? Well, we can't, because it's so hard to ship heat long distances. Furthermore, with Diablo, we can't even live within 5 miles of it. Using cogeneration is best for small distributed generation sources that are close to where people live or where industries are being run. For instance, one of my favorite examples is Coors Brewery in Golden, Colorado. They have their own electricity generation. The waste heat from that is used to brew beer, and then the heat from that, what's left over, is shipped to Colorado School of Mines via a duct that's about 1 kilometer away. And that's about the furthest that people generally ship heat. And so lastly, cogeneration comes in 2 flavors. Normally, or usually, we first generate electricity and use that heat co-product for something else. But sometimes if you want very intense heat, like to melt steel, you'll first use the heat to melt the steel, and then as the steel cools, you can drive a Rankine cycle and generate electricity from that heat. So we can look at the decrease in carbon intensity of our energy over the years. Let's take a look at this graph. As a function of years, we're looking at tons of carbon emitted per tons of oil equivalent. And so in fact, it's not CO2 per energy use, but carbon. And so we look oil, because it's tons of oil. Oil is 84% carbon by weight. And so it makes sense that if you burn 1 ton of crude oil, you're going to get 0.84 tons of carbon emitted in the air in form of carbon dioxide. But the most important thing about this graph is the decrease from 1.1 to 0.7. And so this means we are generating more useful energy with less carbon emissions, largely because we've moved from wood to natural gas, and also renewables, which emit less carbon dioxide for the same amount of energy. But it's not really energy we want, it's really happiness. So what we want is really a carbon intensity of our happiness. But then the economists say, we're uncomfortable, we cannot measure happiness. So we try to minimize the carbon intensity of our economy. And so what we want to do is minimize the kilograms of carbon dioxide per dollar produced in an economy. And so what is this? This is the carbon intensity of your energy production times the energy intensity of your economy, or the amount of energy needed to make a buck. And so we can minimize this by converting fuel to energy as efficiently as possible and using this energy as efficiently as possible to generate wealth. So it turns out that the energy intensity of our economies decreases as we get richer. And this can be for a number of reasons. One, with our increased wealth and technology, we can use greater efficiency in generating more wealth. But also our economies change. As you get richer, we move to technologies such as software development, and China takes over the production of steel, for instance, which is much more energy intense. The United States, in 190 years, has gone from a GDP in real dollars, these are inflation-adjusted dollars, 1990, from $1,019 per year to about $40,000. And in that process, our energy intensity has gone from 2.5 to 0.5 of kilograms of oil equivalent per US dollar generated. Our per capita energy use did go up by 8, but the per capita income went up by 40. And so our energy use per dollar made dropped by a factor of 5, from 2.5 to 0.5. This is a very famous graph, and we'll see it many times, where we look at the amount of electrical energy used per person per year as a function of the year. Now, throughout this period of time, the United States wealth increased rather monotonically. And we see in particular in California in 1974, just right around the time of embargo, the oil embargo, and the first concern for efficiency, California began invoking a lot of efficiency measures, and the electricity use per person went flat. So our electricity use per person did not increase, while our wealth did increase. And you can see that for the rest of the United States, and in particular, the Republican states did not embrace efficiency the same way, and their electricity use increased. Now, you can always respond, yeah, but it's in those Republican states that they produce automobiles, and there's a lot of heavy industry that are really electricity intensive. So what did we learn real quick? We remember efficiency and recognize that in order to find out what the carbon intensity is of your actual energy use, you need to divide by the efficiency. We learned about cogeneration, that if we can find a use for our heat co-product, it will increase our efficiency greatly and also decrease our carbon intensity. And lastly, we recognize that the carbon intensity of our economy depends on both our ability to burn fuel efficiently and generate energy, as well as use that energy efficiently to generate wealth.